Okay, today I'm going to talk about this asynchronous recorded lecture on sequential bargaining. Okay. Now, previously we had looked at a game of kind of divide the dollar, and I gave you a homework problem on that, on divide the dollar, and that was a simultaneous game. Simultaneous game. You remember that game? Simultaneous game, which was both players simultaneously state their shares. Let's say S1, S1 and S2, respectively. If S1 plus S2 is less than or equal to 1, then they get their shares. If not, both get 0. Now we know in this game, all S1, S2 greater than or equal to 0 such that S1 plus S2 equals 1 are Nash equilibria, right? The logic is pretty straightforward. The intuition is, let's say player 1 says 70. What's player 2's best response? Well, player 2's best response is to say 30, because anything else will give you less than 30, or if you say more than 30, it's going to be 0. So 70-30 is a Nash, because if I say 30, then what's your best response? It's 70. But there's a continuum of Nash. If I say 80, your best response is 20, and that's a Nash. And if I say 20, your best response is 80, that's a Nash. So in some ways, that's a somewhat unsatisfactory game, right? Unsatisfactory because you really don't know what will happen in this very fundamental question. How do you divide a dollar? Okay, so what we do is now think of this as a sequential game. A sequential game is not very, it's very interesting, but, tell me what you think. So sequential game is player 1 moves first. Player 1 moves first, asks for S1. Player 2 observes S1 and has an option to accept and keep 1 minus S1, or reject and let's say gets 0. Yeah. So in this case, basically 2 will accept anything that gives her at least as much as her outside option, right? Because which in this case is 0, right? So anything that leaves 2 greater than or equal to 0, 2 will accept. Remember, 2 will accept. If it is 0, then 2 is indifferent, and we know that accepting is the best response. So what is player 1 going to do? Player 1 knows this. Player 1 knows what 2 will do. So she maximizes her utility by doing what? By keeping everything. So S1 equals 100, S2 equals 0, 2 accepts, because indifferent between accepting and rejecting. Unique SPNE, subgame perfect Nash equilibrium, 100, 0. 1 extracts all the surplus. In common parlance, 1 has all the bargaining power in this game. Yeah? Okay. So essentially, the reason this is happening is because of the take it or leave it nature of this game. 2 doesn't really have. 2 can only accept or reject. 2 can only accept or reject. So this is not really what I would call a bargaining game, because 2 is not allowed to bargain. Yeah. So how should we amend this? So how should we amend this? We can do 2 things. Well, let's start with, for the first one, we can allow 2 to reject and make a counteroffer. That, I think, is the essence of bargaining. Because now 2 actually has some response, except rather than just saying, okay, take it or leave it, right? So I think that's what we will do. We will amend this game to allow 2 to have that bargaining power by giving her an option to reject and make a counteroffer. So the minimum periods that I need is 3, right? Which is period 1 makes an offer, 2 can reject, make a counteroffer in period 2, and then so on. We can keep on adding periods. We can keep on adding periods in the same pair kind of way, in the same structure, like period 1 and 2 can continue in the same vein. So the game can continue potentially indefinitely, right? Indefinitely. So that's how we're going to modify it. And I'm going to do a 3-period game. And the point is that the 3-period game, I'll be looking for a 3-period alternate offer bargaining game. And I'm looking for a subgame perfect Nash equilibrium in this game. Okay, so I'll kind of define this game. explicitly in the next step, and we'll move forward. I want to note one thing here, though, which is really important, right? Because in our game, this unique subgame perfect Nash equilibrium, we got this S2 equals 0 is because that's what the outside option was, right? What if the outside option, what if the outside option for 2 was 20? Then we know, and one knows, that any offer that leaves 2 below 20, 2 will reject. Okay? If the outside option was 30, then 30 is the floor. So basically the outside option, so which is what happens if we don't come to an agreement. If we don't come to an agreement, what happens if we don't come to an agreement has a big influence, effect on the agreement itself. Okay? So that in some ways is kind of an essence of bargaining power, right? If I can do better outside the bargain, I can do better inside the bargain. Just remember that. This is one of the life lessons in terms of bargaining. Okay, now let's look at this 3-period game, okay? So the 3-period game is period 1. 1 makes an offer, and the structure is S1, a share for herself, and offers 1 minus S1. So it's dividing $1, right? 1 minus S1 for player 2. So that's the player 1's offer, okay? Now, player 2 can accept, and the game ends, okay? However, this is a bargaining situation. Player 2, if player 2 rejects, the game continues. That's really the key difference from the previous one, right? The game continues to the next period, which is period 2. Now here in period 2, I want to stress one very important part. What we introduce is discounting. Okay, so both players 1 and 2 discount over periods. You know what discounting means, right? They have discount factors. Let's call them discount factors. Delta 1 for player 1, delta 2 for player 2, which is how much you discount the future, i.e. delta 1, delta 2 are both less than or equal to 1. So typically delta 1, which we call the discount factor, what you have seen it before in either finance or micro, what we typically call is 1 over 1 plus R, right, which is the interest rate. So this is how much we discount the future, right? So something 1 period from today, X, 1 period from today is worth delta X today. And 2 periods into the future is worth delta square X today in today's dollars, right? So this is the present value. And since delta square is less than delta, as delta is less than 1, things far out in the future are worth less from today's perspective. And in our framework, that creates an incentive to make a deal sooner rather than later. Yeah? So we are going to have discounting between periods, and we'll talk more about discounting as we move along. So period 1, just to recap, 1 makes an offer, S1 for herself, 1 minus S2 for player 2. If player 2 rejects, game moves on to period 2, where player 2 makes an offer, S2 for herself, and 1 minus S2 for player 1, right? So now it's her turn. 1 can accept and the game ends. As before, or reject and the game goes on to period 3. So I need a minimum of 3 periods for this game to be interesting. Period 3, what happens? Well, nothing happens in period 3 except both parties get exogenously determined shares. S bar for player 1 and 1 minus S bar for player 2. So the game ends. So everybody knows, right? If you get to period 3, this is what's going to happen. Nobody has any choices anymore. And the key is that between period 2 and period 3, there is discounting, delta 1 and delta 2. And between period 1 and period 2, there's discounting. I'm allowing both players to have different discount factors, okay? So you know, I could be playing against you, and you are very patient. Your delta, you know, remember, right? You're very patient, which means you value the future as much as the present. So you can wait, is if your delta is close to 1. If your delta is really small, that means that, you know, a deal in the future is worth very little today. So that's how you have to play with the deltas. Okay, so we will look for a subgame perfect Nash equilibrium, and I will show there is actually a unique subgame perfect Nash equilibrium. And as it is typical in these games, we solve by backward induction. Okay? We solve by backward induction. So let's solve by backward induction. How do we do it? So let's start with the period 2, because period 2 is where the last choice is made, right? Period 3 is nothing happens in the sense of players' choices. Let's start with period 2, okay? Okay, let me just, okay, so, okay. So in period 2, player 2 is making an offer, right? She knows, right, that any offer she makes, 1 can reject wait a period and get S bar, right? That's the nature of the game. The value of that S bar, this is in period 3, from period 2's perspective, right? Remember, we are in period 2. From period 2 perspective is what? For player 1. So what is the value for player 1, right? S bar 1 period from now is worth how much today? Well, we know how much it is. It is worth delta 1, which is your discount factor for player 1 times S bar. So 2 cannot offer 1 anything in period 2 less than equal to, well, less than delta 1 times S bar, because 1 will reject. Because 1 will reject. So 2 offers delta 1 S bar to 1 and keeps for herself the rest, which is 1 minus delta 1 S bar. Okay? And we know 1 will accept, because 1 is indifferent between accepting delta 1 S bar or rejecting and getting getting S bar next period, which is worth delta 1 S bar today. For sum game perfection, I need to know, will 2 make this offer? Which means 2 gets 1 minus delta 1 S bar. But if 1 rejects, what does 2 get? 2 gets 1 minus S bar next period, right? I mean, so I'm trying to ask, will 2 make this offer? We know she gets this much if she makes the offer. If it doesn't, if 1 rejects, then the game goes to third period where 2 gets 1 minus S bar. But from today's point of view, I have to discount it. It's just this much. So 2 will make this offer if this is the case. Yeah? So 1 minus delta 1 S bar is greater than equal to delta 1 minus S bar. Okay? Now is this inequality true? Yes, this inequality always holds. Why? Because you can think about it, just manipulate it, right? It is 1 minus delta 2 is greater than equal to delta S bar delta 1 minus delta 2. I'm manipulating it, right? So just distribute here and collect terms. And this is always true, right? Because you can write this as 1 times 1 minus delta 2. I know 1 is always greater than S bar because S bar is a share, remember? So 1 is always greater than S bar. And since 1 is also always greater than delta 1, remember delta 1 is a discount factor. Delta 1 is always less than equal to 1. So therefore, this number is bigger than this, and this number is bigger than this. So this inequality always holds. So yes, so you've solved the game from period 2 onwards. From period 2 onwards, 2 offers to 1, how much? Delta 1 S bar, keeps for herself 1 minus delta 1 S bar. So, okay. So if the game gets to period 2, this is what's going to happen. We know that. So let's now go to period 1. Yeah. So now 1 is making the offer, right? So 1 says, this is what 1 thinking, right? 1 says he has to make 2 an offer at least worth what? So think about it, right? He has to make 2 an offer at least worth 1 minus delta 1 S bar in period 2, which is in period 2 because anything less has to make an offer in period 1, which is worth at least this much in period 2. So this is period 1, because otherwise anything less, 2 will reject, get to period 2, and make 1 minus delta 1 S bar, right? So what? So which means from period 1's perspective, 1 has to offer to how much? To be indifferent between accepting and rejecting. 1 has to offer 2. Remember, from a period 1 point of view, delta 2, 1 minus delta 1 S bar. This is second period payoff, second period settlement, let's call it, and from today's point of view. So 1 has to offer 2 this. If 1 offers 2 in period 1, remember we are talking in period 1, delta 2, 1 minus delta 1 S bar, 2 is indifferent between accepting and rejecting, okay? So the equilibrium offer is 1 offers 2, 1 minus delta 2, 1 offers 2, delta 2, 1 minus delta 1 S bar, and keeps for herself. How much? Is 1 minus delta 2, 1 minus delta 1. The rest, right? Whatever is left over after this, which is 1 minus that. So that's what we propose is the equilibrium. If 1 offers this, 2 will accept. And the game ends. So the game doesn't continue now, right? Even though it could continue up to period 3, game ends in period 1, okay? That's a pretty nice point, right? Which is saying the game ends right away. The question is, subgame perfection, will 1 make this offer? 1 will make this offer if 1 minus delta 2, 1 minus delta 1 S bar is greater than or equal to what? What's the alternative? The alternative is 2 rejects, and then 1 rejects, and you get to S bar, and discounted 2 periods now, right? S bar is in period 3, reject, you get to S bar, 2 periods now. What's the value for player 1? It's delta 1 squared, right? It's 2 periods before. If this is true, 1 will make that offer. Using the previous logic that I did in the previous inequality, you can show that this is true. Actually, all I need is, delta 1, delta 2 less than or equal to 1, and S bar less than or equal to 1, right? That's all I need. It doesn't matter on the relative values of delta 1, delta 2. Why don't you do this as an exercise? It is true. Exactly the same logic as I did before. So I have found a unique subgame perfect Nash equilibrium because 1 will make this offer. So which is 1 minus delta 2, 1 minus delta 1 S bar, and delta 2, 1 minus delta 1 S bar for player 2. 1 makes this offer. 2 accepts instantaneously. Game ends. Period 1. Nice result, right? Because even though the game can continue potentially longer, I can make this not just a 3-period game, but a 5-period game, 7-period game, 9-period game, 11, as long as you want. Finite game, very long, work backwards, exactly the same logic. The formula becomes more complicated, but game will end in period 1 with exactly the same logic, right? Which is indifference between periods. So this was kind of the Rubinstein's alternate offers bargaining model. It's really nice. You get it. So the point is, let's make some points here. Number 1, efficient. The solution is efficient, right? I mean, discounting means that an agreement today is better than an agreement tomorrow. So here you get or even tomorrow, right? So in this game, this is efficient because there is no delay. So very nice, right? No delay. There's nothing that they should have a delay. Second, let's just do two derivatives, right? So if this is S star, which is what player one gets in equilibrium, S star, let's say, is player one in equilibrium, then ds star d delta 1 is positive. Just do the derivative, right? Which is, d1 minus delta 2. This is player 1's, right? S star is, let's say, player 1's. ds 1 minus delta 2, 1 minus delta 1 S bar over d delta 1, which is equal to plus delta 2 S bar, right? Which is greater than 0. What does it mean? As delta 1 goes up, you're getting more patient, right? Closer to 0, closer to 1 is more patient, which means future is valued as much as almost the present, right? I mean, this is as delta goes up, you're more patient. You value the future more. You don't see the decay in the future if you have a deal as almost the present. So what does that mean? That means you can extract a better deal. Essentially, what you're saying is, this is credible, right? Because you basically say, if 2 makes you an offer, you're basically saying, listen, delay is not that costly to me because my delta is pretty high. It's close to 1. So I'll just wait. I'll reject. Now, whatever is, that puts pressure on 2 because now she says, man, I have to make her a better offer. Keep less for myself. So 1 benefits. The converse is true for the other guy, right? The converse is true for the other person's discount factor. The more patient your opponent is, the worse off you are in equilibrium. In equilibrium. Finally, the same as before, the better is your outside option, S bar, the better is the equilibrium solution. The better is your inside equilibrium, right? Which is ds star ds bar is greater than 0. I think this is kind of the big truth. Okay? So I think that as far as I'm concerned, this kind of covers most of the things I want to talk about bargaining. And I'll give you a couple of homework problems on this. And I think the logic is pretty nice. The extensions include making this into an infinite horizon game. When I talk about infinite horizons, I'll talk about what really happens there. But otherwise, this is a nice kind of compact, self-contained lecture. Okay, I'll see you folks later.